Tonight, we're going to explore why landing humans on Mars may be impossible with any technology we have ever flown. Reaching the planet is only half the problem. The spacecraft still has to lose thousands of kilometers per hour and place a crew, their supplies, and return vehicle gently onto the surface. Mars offers almost nothing to help. Its atmosphere is less than 1% as dense as Earth's. That makes it thick enough to strike a heat shield at nearly 6 kilometers per second and produce destructive heat, but too thin to slow a heavy spacecraft before it reaches the ground. Every successful Mars landing so far has delivered a robot weighing roughly a ton or less. A human mission may require landing 20 to 30 tons at once. At that scale, the parachutes, airbags, and sky cranes that worked before are no longer enough. The vehicle would have to ignite powerful engines while still moving at supersonic speed. Its computers must identify safe ground, control the descent, and land without help from Earth, because the entire sequence is over before mission control can respond. There is no runway, no second attempt, no pilot who can circle around and try again. With the landing systems humanity has actually tested on Mars, a crew-sized vehicle cannot yet be placed safely on the surface. By the end of tonight, you're going to understand why the Martian atmosphere creates the worst possible landing problem, why scaling from a 1-ton rover to a human spacecraft changes everything, and what must be invented before the first astronauts can touch the ground. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. The Romans named the fourth planet after their god of war because of the way it burned red in the night sky. Ares to the Greeks, Mars to Rome. A world the color of dried blood, wandering against the fixed stars in a pattern that marked it as different long before anyone understood what a planet was. Centuries later, the first telescopes found more than a reddish point. Astronomers saw polar ice caps growing and shrinking with the seasons. They saw dark markings that seemed to spread and fade across the surface. For a time, some of the era's most serious scientific minds convinced themselves those markings were canals, engineered waterways built by an advanced civilization carrying water across a dying world. Maps were drawn, papers were published. Observatories devoted years to tracing lines that were never there. The canals were an illusion, created by small telescopes, tired eyes, and a very human eagerness to find purpose in blurred details. But the desire behind the mistake never disappeared. Long before rockets or powered flight, people were already asking whether Mars held someone, or whether it could someday hold us. That question is no longer confined to observatories or science fiction. It has funding now. NASA is developing technologies intended to support human missions to Mars as early as the 2030s. SpaceX is building Starship around the long-term goal of carrying large amounts of cargo and eventually people to the planet, with its public Mars plans listing initial cargo missions no earlier than 2028. China, meanwhile, has successfully orbited, landed and operated a rover on Mars, and is developing the next stages of its robotic exploration program. Different programs, different stages, one destination. What does it take to even say a date like the late 2030s? Rockets years into development. Launch sites built and rebuilt. Habitats designed, tested, and redesigned. A workforce numbering in the tens of thousands, spread across agencies and contractors on 3 continents, each piece of that machine pointed at the same red dot in the sky. This is not a hobby project or a thought experiment. It is one of the largest coordinated technical undertakings currently happening anywhere on Earth. Setting foot on another planet is no longer only the material of science fiction, the province of novels and film. It is a stated objective of governments and private companies with billions of dollars behind it, and the most capable spaceflight technology human beings have ever built. Reusable rockets that land themselves, advanced life support systems that recycle air and water, decades of accumulated orbital experience, learned the hard way, mission by mission, failure by failure, correction by correction. All of it aimed, at least in public statements, at the same red point in the sky the Romans once named for their god of war, the same wandering light that convinced earlier generations of canals and civilizations that were never actually there. So why even ask whether it is possible? The rockets exist. The funding exists. The stated will exists at the highest levels of 3 separate space programs, each with its own reasons for wanting to be first. But here's the problem. Wanting something badly does not change what the universe allows. Brilliant engineers and enormous budgets can design a rocket capable of the trip, can solve for thrust and fuel and trajectory with tremendous precision. They cannot negotiate with physics. Not a funding question, a physics question. And physics has a great deal to say about a journey to Mars, most of it inconvenient, some of it close to unanswerable with the technology that exists today. That is not a story about failure. It is a story about evidence, examined one obstacle at a time, in the order the universe presents them. Some of the obstacles compound, stacking onto one another until a mission carries risks no single hazard would explain on its own. Some, once triggered, cannot be undone, no matter how skilled the crew or how well funded the agency behind them. Whether they can be solved before a crew is asked to risk everything on the attempt is the real question sitting underneath the stated goals and the launch dates. Think about what those timelines actually assume. Every announced schedule from NASA, from SpaceX, from the Chinese National Space Administration quietly assumes the human body and the human mind can simply endure whatever years of travel and isolation demand of them. That assumption has never been tested at the distances and durations a real Mars mission requires. Nobody has spent years cut off from Earth the way a Mars crew would be. Nobody has absorbed the radiation dose, weathered the toxic dust, or lived through the total, unbroken confinement such a mission forces, not all at once, not layered on top of each other the way an actual mission would layer them. The plan is built on hope stacked over incomplete data, and the space between hope and data is exactly what the rest of this examination is about. None of this makes the ambition foolish. Humanity has crossed oceans it could not swim, and skies it could not breathe by first asking hard, unwelcome questions about the gap between wanting and doing, then closing that gap piece by piece. Mars may eventually be no different, but the honest way to find out is not to repeat the confidence of the announcements. It is to walk through what actually stands in the way, obstacle by obstacle, and let the evidence speak for itself before the funding does. This is not a single wall to climb. It is a sequence, each obstacle changing what the next one costs, each one testing a different part of what a human being is. Distance changes what rescue means. Radiation changes what the body can absorb before the mission has even properly started. Dust changes what breathing means. Gravity, or the near total absence of it, changes what the skeleton and the heart can be trusted to do. And isolation changes what the mind can be trusted to do right at the moment clear thinking matters most. None of that is stated yet as fact. For now, hold it as a shape, a promise of how these obstacles will turn out to relate to one another, worth watching for as the evidence accumulates. The first obstacle does not look like an obstacle at all. It looks like a number, the kind most people would say they already understand. A distance. It does not sound dangerous. That is exactly what makes it worth sitting with first. A number that doesn't sound dangerous is still worth taking apart slowly. The word carrying this one is the problem. Distance is the same word used for a walk to the corner store or a flight across an ocean, and the mind reaches for those categories automatically. An ocean crossing takes hours by plane, weeks by ship if it has to. Mars refuses to fit inside either of those boxes. It is not far the way anything on Earth is far. It is far in a way that starts to bend the intuitions most people carry about travel before the first number even lands. At its closest, which happens only briefly, roughly once every 2 years, Mars sits about 54 million kilometers from Earth. Picture driving there instead of flying. Not a rocket, not an orbit, just a car, holding a steady highway speed of about 100 kilometers an hour, never stopping to sleep, eat, or refuel. That drive would take roughly 62 years. Longer than most careers, longer than most marriages, longer, for a lot of people listening to this, than the life they have lived so far. And that number assumes the closest possible moment, the one narrow window every 2 years when the two planets happen to line up on the same side of the sun. The rest of the time, they do not cooperate. Earth and Mars are both circling the sun on their own separate clocks, at their own separate paces, drifting apart for most of every 2-year cycle before briefly swinging close again. How do you hold a number like that in your head? Not directly. Nobody actually feels 54 million kilometers, or 400 million. The brain needs something to translate it into first. At its farthest, Mars sits more than 400 million kilometers away, nearly 8 times the close approach distance. Earth's own circumference is about 40,000 kilometers. At that farthest point, Mars is more than 10,000 trips around the entire planet away, stacked end to end. Stretch that same imagined highway drive to match, and the trip climbs past 4 centuries behind the wheel. 400 years of steady driving, and the destination still has not arrived. Distance to Mars is not a fixed fact carved into the solar system. It is a range that swings by hundreds of millions of kilometers, depending on where each planet happens to be sitting in its year. Which means the very question, how far is Mars, has no single answer at all. Spacecraft do not drive, of course. A vessel bound for Mars with current propulsion cruises at somewhere between 20 and 24 kilometers a second. Put that next to something ordinary. A commercial jet cruises at somewhere around 1/4 kilometer a second, and a rifle bullet, one of the fastest objects most people will ever picture, crosses roughly 1 kilometer in a single second. A Mars-bound spacecraft moves close to 100 times faster than that jet, and 20 to 25 times faster than that bullet, sustained hour after hour, for months at a stretch. And even at that speed, the trip is not quick. One way still takes between 7 and 9 months, longer than a full school year spent inside a sealed vessel with the same handful of faces and the same recycled air. A full mission out to Mars, time spent on the surface, and the trip home runs somewhere between 2.5 and 3 years total. That is roughly the length of a graduate degree, except every class, every meal, and every night's sleep happens inside the same few rooms, with no weekends away and no visitors. 2 to 3 of those years are spent entirely in space, or standing on a world that is not Earth, sealed away, cut off, with no shortcut home, and no way to simply turn around partway and come back sooner. There is no highway exit on the way to Mars. But here's where it gets strange, and it is not because any of these numbers change, it is because of what they mean once they sit next to something familiar. The International Space Station orbits about 400 kilometers above the ground. Cosmically speaking, that is right next door, closer to the surface than many commercial flights ever climb. A capsule sits docked and ready at all times, specifically for emergencies. If a system fails up there, controllers in Houston or Moscow are already on the line within seconds, working the problem in real time alongside the crew, and if it is serious enough, that crew can be back on Earth within hours. A Mars crew has no version of that safety net. Not seconds, not hours, not even days in the way a stranded sailor might once have waited for a passing ship. Months, if a return is even possible at that point in the journey, and often nothing at all. That is the real shift distance forces onto the mission. It does not just make the trip long, it removes the rescue option completely, for years at a time, and it does so quietly, without ever changing the design of a single rocket engine. Think about what that erases. A fever that will not break, a broken bone set wrong the first time, a piece of equipment failing in a way nobody predicted during testing. On the space station, any of those is a serious problem with backup close at hand, a capsule ready, a ground team responding in minutes, a hospital reachable the same day. On the way to Mars, or standing on Mars itself, the exact same problem has to be solved entirely by the people it is happening to, with whatever tools and training are already on board, because nothing is coming and no one can arrive in time to matter. Every decision becomes a decision made alone. That is what the distance actually buys, beyond the miles. Not an inconvenience measured in extra travel time. A complete redefinition of what danger means once help stops being minutes or hours away and becomes, at best, a wait of months, and at worst, an impossibility built directly into the orbital mechanics of two planets that refuse to hold still for anyone. Is a mission like that dangerous simply because it is far? Not exactly. It is dangerous because of what far removes. No fast rescue, no same-day evacuation, no ground team a short flight away. Distance alone, without a single additional hazard added on top of it, is already enough to make a Mars mission one of the most dangerous undertakings in human history. Every other risk examined from here forward gets layered onto a foundation where help, in the way every astronaut before this has understood help, simply does not exist. Every hazard still to come has to be survived on that same foundation, alone, with whatever the crew already carries with them. And this is still the smallest of the obstacles waiting in this examination. Distance looks like a fact everyone already understands. A big number attached to a reddish point of light. People have watched since before telescopes existed. Sit with it a while longer, and it stops being a number at all. It becomes the condition every other hazard on this journey has to operate inside. The quiet fact that whatever happens next, out there, has to be handled alone, by whoever is standing closest to the problem when it starts. What that same distance does to something as ordinary as a conversation with home is where the next problem begins. That gap does not only erase the chance of rescue, it reaches into something smaller and more ordinary too. The plain act of talking to another person back home. A voice leaves the spacecraft and starts across empty space at the fastest speed anything can travel. The speed of light itself, and even that speed is not fast enough to make the gap disappear. One way, the trip takes between 4 and 24 minutes, depending on where Earth and Mars happen to sit in their orbits at that moment. 4 minutes is roughly the time it takes to boil an egg. 24 minutes is roughly the length of a half-hour television episode, minus the parts nobody bothers to watch. Send a message home at the near end of that range, and you could boil the egg twice before an answer starts back the other way. Send it at the far end, and the reply is still crossing space when the episode has already ended. That is one direction only. A real conversation needs two, and light does not care how badly anyone wants to hear back sooner. You ask something, and you wait. The answer comes, and by then the situation on your end has usually moved on, so you ask again, and you wait again. There is no interrupting. There is no talking over each other, no quick clarifying question tossed back in the same breath. Every exchange has to be written whole, sent, and left alone to travel. Send a question, and the earliest a response can possibly arrive is about 8 minutes later, and only if Mars and Earth happen to be sitting close together that season. In the worst arrangement, a single round trip, question out, answer back, takes nearly 45 minutes, roughly the length of a long lunch break, spent waiting on one sentence. What does a crew do with a gap that size sitting in the middle of every decision? Mostly, they stop asking. Mission Control can advise on the slow, careful choices made days in advance. It cannot referee the fast ones. Whoever is standing in the room when something breaks has to be the one who decides what happens next, because by the time an answer arrives from Earth, the moment it was needed has usually already passed. Picture what that does to an actual emergency. A pressure reading looks wrong. A pump stutters and stops. An astronaut radios the words every mission dreads. We have an emergency, and then waits. Not for a callback. For as long as it takes light itself to cross tens of millions of kilometers and return, carrying nothing yet but the confirmation that the message arrived. But here's the part that is harder to sit with. Troubleshooting a failing system with the one person who can help sitting 45 minutes away, each way, is not a slower version of the same job. It is a different job entirely, closer to diagnosing the failure alone, closer to treating a voice from home as a distant second opinion that only arrives long after the moment it could have mattered. And that delay, as bad as it sounds, is the mild version of the problem. Wait, there is a stretch of every mission when the delay does not just get worse, it disappears into nothing at all, because nothing gets through. NASA's Mars campaign director, Dana Ives, has called it the single most troubling problem the agency faces. More troubling even than the minutes-long lag itself. Roughly every 26 months, Earth and Mars swing around to nearly opposite sides of the Sun, an alignment called solar conjunction. Radio signals cannot pass through the Sun. Charged particles boiling off its surface scramble anything that tries to sneak past close by. Not slowed, cut off completely. For close to 2 weeks at a stretch, a crew on Mars becomes entirely unreachable. No messages arrive. No instructions come down from mission control. No emergency channel sits open in the background as a fallback, waiting to be used if things go wrong. If a system fails during that window, the people on the ground hundreds of millions of kilometers away cannot help, cannot advise, cannot even confirm they heard the call go out. Whatever breaks during those 2 weeks gets diagnosed and repaired, or it does not, entirely by whoever is standing closest to it when the alarm sounds. Engineers are already working on ways around it, and the research is genuinely promising. Relay satellites positioned at special points in space, spots where the pull of the sun and the pull of a planet balance out enough that a spacecraft can sit there and simply stay put without drifting away, could shrink that 2-week blackout down to a few scattered hours instead of 14 silent days. Laser communication, sending data as pulses of light rather than radio waves, is already being tested aboard NASA's Psyche spacecraft, and it could move far more information through the same narrow gap in far less time. Both ideas show real promise. Neither is built, tested, and flying at the scale a crewed mission would actually need. A relay point tested in isolation is not the same as a habitat depending on one during a real failure, years from now with lives attached to the outcome. The blackout, for now, remains unsolved. And even if every relay satellite and every laser link works exactly as planned, something underneath the blackout still does not go away. Not a technology gap. Physics itself. Light only moves so fast, and no amount of funding, no clever engineering, no future breakthrough changes that one number. The 4 to 24 minute delay is permanent, built into the distance between two planets that were never going to hold still for anyone's convenience. Solving the blackout would only remove the worst 2 weeks of a problem that never fully leaves. Researchers take the toll of that seriously, and they have already measured some of it, using people who never left Earth at all. In 2010, 6 volunteers sealed themselves inside a mock spacecraft built in Moscow and stayed there for 520 straight days, a project called Mars 500, built specifically to study what growing isolation and a lengthening communication lag do to a small, closed crew over time. Alongside separate studies of submarine crews cut off for months underwater, and researchers wintering over in Antarctica through months of darkness, the pattern held steady across every group. Depression that deepened the longer isolation stretched on. Sleep that would not settle into a normal rhythm. Small conflicts between crewmates that grew sharper instead of fading with time. Decision-making that grew measurably slower and less reliable the longer the isolation continued. Those volunteers still had sunlight somewhere outside their sealed building. They still had a working phone line to family, however delayed. They still had, in a genuine emergency, a door they could walk through. A real Mars crew has none of those options. What that difference actually does to a person, months into a mission, with no sunlight, no door, and a conversation with home that arrives half an hour late on a good day, and not at all on a bad one, is not something anyone has been able to measure yet. The honest answer is that nobody fully knows, and the simulations that come closest were always missing the one variable that would make them accurate. Something else was already waiting in that same silence, and it had been there since long before the first conjunction ever began. It did not need the sun to block a signal. It had been moving through the ship since the moment it left Earth, and it never once needed anyone to notice it. Radiation does not knock. It does not warm the skin, or sting the eyes, or leave any mark a crew member would notice in the moment. From the instant a spacecraft crosses the edge of Earth's magnetic shield, it works on the body like a slow, invisible fire, present in every hour of the transit, and felt in none of them. This was the second of the 5 obstacles, and unlike the first, it did not announce itself as a boundary to cross, a line on a map, a number on a screen. It was already inside the ship before the ship had even left the ground. Not the radiation of a reactor, humming behind warning signs and thick concrete walls built specifically to hold it back. The radiation of deep space itself, ancient particles that have been crossing the galaxy for millions or billions of years, arriving now at a speed nothing built by human hands could ever hope to catch or outrun. Earth spends its whole existence wrapped in two separate layers of protection against this. The first is the magnetosphere, an invisible magnetic shield generated deep inside the planet, bending and deflecting charged particles long before they ever reach the ground. The second is the atmosphere sitting above it, a blanket of gas roughly 100 kilometers deep, about the driving distance between two mid-sized cities, thick enough to absorb and scatter almost everything that slips past the first layer. Together, the two hold what a person on Earth actually absorbs down to something small, roughly 2 to 3 millisieverts a year, the rough equivalent of 20 to 30 ordinary chest x-rays, spread across 12 months. The body evolved inside that faint trickle for billions of years. It has no comparable defense built in for what waits on the other side of it. Leaving that shelter changes the arithmetic entirely, and for a long time nobody actually knew by how much. Early estimates were models, built on assumptions and educated guesses about what deep space would deliver to a human body over months of exposure. Guesses are not measurements. Then, in 2012, NASA sent something that could simply measure it directly. The Curiosity rover launched toward Mars aboard the Mars Science Laboratory, carrying an instrument built for exactly one purpose, the Radiation Assessment Detector, known as RAD, designed to record what a real traveler crossing that distance would actually receive, not what a model predicted they might. The trip took 153 days. RAD logged a total dose of around 0.3 of a sievert, 300 millisieverts, for that one-way crossing alone. Set that against NASA's career limit, the total dose an astronaut is permitted to absorb across an entire working life, somewhere between 0.6 and a full sievert depending on age and biological sex, calculated to keep the added lifetime risk of fatal cancer under 3%. Narrated slowly in household terms, a full career's allowance works out to something like 60 to 100 CT scans, spread across decades of missions and a working lifetime. A single one-way trip to Mars spends about 30 of those scans in 5 months, before a boot ever touches the ground. The return trip spends roughly as many again. Add the two halves of the journey together and 2/3 of a lifetime's allowance is already gone, just getting there and back, and that is before a single day is counted on the surface itself. The dose does not arrive as one steady, even drizzle. It comes in two distinct forms, and the two behave nothing alike. The first is solar energetic particles, bursts of charged particles, mostly protons, thrown outward by flares and eruptions on the sun's own surface. These give little warning. During a serious event, the radiation level can spike within minutes, and inside a lightly shielded spacecraft, a burst of that size could deliver a lethal dose in a matter of hours, not months. The second is galactic cosmic rays, the scattered remnants of stars that finished exploding long before the sun ever ignited. Particles accelerate to nearly the speed of light over millions of years, and arriving now from every direction at once, with no pattern, no forecast, and no warning siren to precede them. One threat waits for a trigger somewhere out on the sun's surface. The other never stops, and never needs one. How do you guard against a danger with no schedule and no direction? You cannot watch the sky for it, the way you might watch for a coming storm, because it is already arriving from every point in the sky at once, day and night, whether anyone is watching or not. At the cellular level, that difference matters more than it sounds like it should. A single high-energy particle from a galactic cosmic ray, striking the DNA double helix, does not leave one clean break the way ordinary radiation usually does. It tears through several strands at once in the same small stretch of genetic material an injury researchers call complex cluster damage. Picture the cell's repair machinery as something built over billions of years to fix one clean cut at a time. Now picture it handed a tangle instead, several breaks knotted together in the same tight space. It was never designed to read wreckage like that. Ordinary radiation causes single breaks the body usually mends without much trouble. This causes multiple breaks, layered on top of each other, often left unrepaired entirely. Not sunburn, not simple fatigue that fades with a night's rest. A rewriting of the genetic code itself, one cluster of breaks at a time, and the body has no reliable way to undo it once it has happened. And the damage does not stop at the level of the cell. NASA-funded research, using animal models, has already shown that radiation matching the deep space kind causes measurable harm to the brain itself. Mice exposed to the same heavy ion radiation a Mars crew would absorb showed real neurological impairment, trouble with memory, with learning, with decision-making, along with heightened anxiety responses that persisted well after the exposure itself had ended. A 2016 study published in the journal Scientific Reports from researchers at the University of California, Irvine, found that this kind of radiation caused lasting inflammation in the brain and measurable disruption to the signals neurons use to communicate with each other. What looks, on paper, like a cancer statistic turns out to also be a statement about memory, mood, and the steadiness of a person's hands. Here is what that means laid against the actual timeline of the mission. Over those same 7 to 9 months of transit, a crew's brains are being struck from every direction, day and night, with no pain and no visible symptom to mark any of it happening. And yet, underneath that silence, cellular and neurological changes are already accumulating quietly. Changes that can blunt judgment, slow reaction time, and unsettle emotional control well before anyone notices. That erosion is not landing on some quiet, uneventful stretch of the mission where it would matter least. It is landing directly before the hardest few minutes of the entire journey, the descent through a thin, unfamiliar atmosphere, and the final seconds of finding solid ground beneath the ship. The mission asks for its sharpest thinking at the exact moment it has spent months quietly dulling the instrument that thinking depends on. 3 obstacles still waited beyond this one, each with its own timeline and its own quiet demands. One buried in the dust underfoot, one working against the body through its own slow decline, one settling, more quietly, into the mind over months of confinement. Radiation was only the first of them already moving through the ship, unfelt, unannounced, impossible to switch off with a flipped breaker or a closed hatch. The instinct, faced with something that reaches you straight through solid walls, is to build a thicker wall. Whether that instinct could actually hold against a particle moving at nearly the speed of light was the next question the mission would have to answer. And the answer was not going to be simple. The instinct is a simple one. Something is coming through the walls, so make the walls thicker. Add mass, add plating, and whatever is outside stays outside. That instinct works for almost every hazard a spacecraft carries. Against galactic cosmic rays, it can backfire completely. A single high-energy particle from deep space, striking a thin wall, might pass straight through it or stop cleanly somewhere inside. Send that same particle into a thick wall of heavy metal instead, and something stranger happens. At those energies, the particle rarely just stops. It slams into the atoms of the shielding itself, and the collision throws off a spray of new particles, a secondary shower scattering outward from the point of impact. The original particle is gone. In its place sits a cluster of smaller ones, still carrying energy, still capable of tearing through tissue on the other side of the wall. Depending on the material, adding more shielding can mean absorbing more radiation, not less. How do you guard against a particle that turns the very thing meant to stop it into more of the problem? Not protection anymore. A source of the danger it was built to block. This is why a thicker metal hull is not the clean fix it looks like on paper, and engineers have chased 3 different answers instead. The first swaps material rather than adding mass. Hydrogen-rich substances, polyethylene plastic, ordinary water, produce far fewer secondary particles when struck, because their atoms are lighter to begin with, and leave less debris behind on impact. NASA has tested water walls, polyethylene panels, and sleeping quarters ringed in water for the highest radiation periods of emission turning the crew's own drinking supply and hygiene water into a second, working layer of protection. These help. They do not solve the problem. Every liter of water or sheet of plastic added to a spacecraft is more mass. And more mass means more fuel to leave Earth's gravity, more fuel to slow down at the other end, and a launch cost that climbs with every added kilogram. A spacecraft cannot simply be wrapped in enough water to make the danger disappear. There is a limit to how much can be lifted off the ground in the first place. The second answer skips material altogether. A magnetic field, generated artificially around the spacecraft, could in theory deflect charged particles the same way Earth's own magnetosphere does, bending them away before they ever reach a wall at all. No wall to build, no water to lift, just an invisible field doing the work at the edge of the hole. Research toward this exists, including work backed by the European Space Agency. But a field strong enough to meaningfully deflect galactic cosmic rays would need to be enormous, and the superconducting hardware required to generate one at that scale, with that little mass and that little power draw, does not currently exist outside a laboratory. A flyable version is years away, possibly decades. But here's where it gets stranger. The third answer gives up on stopping the radiation and goes looking for solid ground instead. Somewhere to stand that already blocks what a wall cannot. That ground turns out to offer less shelter than anyone would hope. Mars once had a global magnetic field of its own. It lost most of it billions of years ago, as the planet's core slowly cooled and solidified, shutting off the internal engine that generates a magnetosphere in the first place. What remains is a planet with no meaningful magnetic shield, and an atmosphere only about 1% as thick as Earth's, a thin smear of gas too weak to absorb what the Sun and the galaxy keep throwing down on it. Landing on Mars does not mean stepping under a roof, it means stepping into the open. In 2012, after Curiosity touched down in Gale Crater, its RAD instrument kept measuring, this time from the surface instead of in transit. The readings settled around 0.66 to 0.7 millisieverts a day, and that number does not even include the occasional spike from a solar particle event, landing on top of it. Set against Earth's own background rate, absorbed quietly over a full year, a Mars surface crew takes in roughly that same year's worth of radiation in 3 or 4 days on the ground. Every few days repeats what an entire year on Earth delivers. A surface stay is not brief enough to make that manageable. Orbital mechanics decide the length, not the crew, and the minimum wait for Mars and Earth to realign for the return trip stretches the stay to somewhere near 500 days, close to a year and a half, sealed under that same thin, radiation-soaked sky. There is no shortening it by choice. The planets move when the planets move. Multiply the daily surface dose across that stretch. Add it to the dose already spent getting there. Add the dose still owed for the trip home. Multiple independent studies, run by different teams using different assumptions, land in roughly the same place anyway. The combined mission total can reach a full sievert or more, depending on how active the Sun happens to be along the way. Not a fraction of a career's allowance. The whole allowance spent in one deployment, sometimes with more still owed after. What that dose actually does to a human body over years, rather than the shorter burst doctors have studied on Earth, is not something anyone can say with full confidence yet. There is no population of Mars veterans to study, no decades of follow-up scans to compare against. The honest answer is a gap, not a number, and admitting that gap matters more than a reassuring guess would. Natalie Sterinsky, a former NASA Human Research Program scientist, has put radiation on a short list of 5 risk categories that have to be resolved before a crewed Mars mission can be called genuinely safe, alongside isolation, distance itself, the closed environment of the spacecraft, and the effects of long-term reduced gravity. Radiation earns its place on that list for a specific reason. It is cumulative. It does not reset between exposures, and once the damage is done, it is essentially permanent. It is also, right now, the one hazard on that list that current engineering cannot simply build its way around. The scientists who say this loudest are not the mission's opponents. Most of them are among its strongest advocates, and they talk about the danger the way a person talks about something they love desperately and want to protect. carefully, in detail, without softening it. People do not spend careers being that precise about a threat they secretly want abandoned. This is precision, not pessimism. That precision has opened a different line of research, one aimed less at the walls of the ship and more at the body living inside them. If the particle cannot be kept out, the thinking goes, maybe the damage it causes can be repaired faster, or resisted altogether. Radioprotective drugs. Gene therapy approaches that target the cell's own DNA repair machinery. Biological treatments meant to make human tissue more resistant to radiation at the cellular level. Early results from some of this work are genuinely promising. None of it is a solution yet. It is a direction, not an answer. And a mission planned for the coming decade cannot simply wait for one to mature in time. So radiation stays what it has been since the moment the ship left Earth's shadow, a hazard that cannot currently be engineered away, only reduced at the margins, and endured everywhere else. It was the second of 5 obstacles, and it does not end cleanly here. It simply hands off to whatever is already waiting in the environment. A crew has to live inside once the ship is gone, and the ground is all that is left. On Mars, that environment starts at the boots. It starts with the dust. The ship is 7 months behind you now, and your boots are finally on solid ground, rust-coloured dirt underfoot, a butterscotch tan sky overhead, and a sun that looks barely 2/3 the size it looks from a parking lot back on Earth. For a while, nothing happens beyond the quiet business of standing somewhere new. Even standing still, a fine coating begins settling across the visor, thin as chalk dust, and it does not brush off the way ordinary dust does back home. Then the wind picks up. A faint hiss starts against the visor, soft enough that it takes a moment to place. Within hours, the sky shifts from butterscotch to something dimmer, a haze thickening as fine reddish dust lifts off the ground and hangs in the thin air. This is not a sandstorm in any sense that word carries on Earth. It belongs to a different category of weather entirely, one that on this planet has swallowed whole continents and blotted out the sun for months at a stretch. That storm is still ahead. For now, the haze stays thin enough to see through, a long amber curtain rather than a wall, and the ground crunches underfoot with a texture closer to fine ash than familiar sand. What matters first is what the dust actually is. For a long time, the answer looked simple. Orbital images for decades had shown red plains and dark patches that shifted with the seasons, and meteorites already sitting in labs on Earth pointed to the same iron-rich rock family. Mostly pulverized rock, mostly iron oxide, the same compound that rusts an old bicycle chain left out in the rain, and the reason Mars glows red from 100 million kilometers away. Irritating if it worked into a seal or a lung, the thinking went, but nothing worse than dirt. In 2008, NASA's Phoenix lander touched down near the Martian North Pole and began analyzing the soil underneath it. It had been sent north to search for buried water ice, not toxic salts, and mission scientists had spent years debating what, if any, chemistry in the northern plains would matter beyond that ice. The soil samples answered a different question than the one they had asked. What it found instead changed the conversation entirely. Perchlorate, not rust, not simple grit. A chemical hazard hiding in plain sight. A chlorine atom bonded to 4 oxygen atoms. The same compound that turns up naturally in a few of Earth's driest places. The Atacama Desert in Chile among them, usually in traces too small to worry about. On Mars, it was never a trace. It sat in the ground at roughly 0.5% to 1% by weight, which means for every 100 pounds of Martian soil, close to a pound of it is perchlorate, orders of magnitude above what counts as a safe level of human exposure on Earth. Perchlorate is a known endocrine disruptor, a substance that interferes with the glands that regulate the body from the inside. It crowds into the same doorway the thyroid gland uses to pull iodine out of the bloodstream, an element the thyroid needs to build the hormones that control metabolism, heart rate, body temperature, and a dozen other quiet processes the body runs without being asked. Perchlorate does not use that doorway properly. It jams it, the way a bent key slides into a lock and still refuses to turn. Without enough of those hormones reaching the body, metabolism slows, fatigue settles in, and mood and clear thinking begin to drift. Chronic exposure, even at low levels, suppresses thyroid function cumulatively, a little more lost with every week of contact, and that loss does not reset between exposures. It only accumulates quietly, alongside everything else a years-long mission already asks of the body. Over a stay that lasts well over a year on the ground, even a slow, low-level drain on thyroid function is not something a crew can simply wait out. And on Mars, contact is not optional. Perchlorate rides in on boots and gloves, sits in the habitat air if a filter ever slips, coats equipment surfaces, and works into the seals of every airlock cycled dozens of times a day. The answer was stranger than expected. Martian perchlorate does not sit quietly waiting to be touched. Research published in 2017 in the journal Scientific Reports from a team at the University of Edinburgh found that the constant ultraviolet light hitting the Martian surface, the high-energy part of sunlight ordinarily filtered out by ozone, unfiltered here by any ozone layer or any real atmosphere, activates the perchlorate already in the soil and makes it more toxic than the same compound sitting undisturbed on Earth. Combined with two other common ingredients of Martian dirt, iron oxides and hydrogen peroxide, that UV-activated perchlorate produced a surface that killed bacteria almost on contact. Could ordinary ground really behave that aggressively towards something as tough as bacteria? The lab results said yes. Not inert dust, not background chemistry, a working disinfectant spread across an entire planet. Less like soil, more like a slow chemical reaction running across the whole visible landscape. For astrobiology, this was fascinating, a plausible reason the Martian surface looks essentially sterile. For a human standing on that surface, it raised a question nobody could yet answer. What does months or years of skin and lung contact with UV-activated, perchlorate-laden dust actually do to a person? The honest answer is we do not fully know. And what the researchers did learn was not reassuring. NASA's own planetary protection scientists have flagged the finding as one more reason the surface cannot be treated as chemically neutral, exactly the pattern this piece keeps circling back to. Real progress in understanding a hazard, followed immediately by a gap in knowing what it actually means for a living person standing in it. The dust is not only chemically hostile, it is physically wrong in a way that matters just as much. Martian dust particles are extraordinarily fine, finer than talcum powder, finer than most dust found anywhere on Earth, and jagged at a microscopic level in a way beach sand never is. Sand on Earth gets tumbled by water and wind for thousands of years until its edges wear round. Martian dust has never had that chance. It stays sharp, angular, small enough to travel deep into lung tissue on a single breath. The closest Earth analogue is silicosis, a slow, progressive lung disease that comes from breathing fine, angular silica dust. The kind that has quietly killed miners and construction workers over years on the job. Nobody yet knows exactly how Martian dust compares to silica inside a human lung. Fine enough, some researchers suspect, to slip past the nose and upper airways' usual defenses entirely and settle straight into the deepest tissue of the lung. But its shape alone, sharp instead of smooth, gives the concern real weight. Put the chemistry and the shape together, and the requirement becomes simple to state and brutal to meet. Standard filtration, built to catch ordinary dust and pollen, was never designed for particles this small or this sharp. Filtration on any crude habitat has to work perfectly, all the time, without exception, because a single failure means unfiltered surface air, thyroid suppressing, UV activated, lung scarring dust, reaching the people breathing inside it. Every piece of equipment that goes outside and comes back in has to be treated as contaminated until proven otherwise, brushed down, sealed, and inspected before it is allowed anywhere near the air the crew breathes. That perfection has to hold for years, checked and rechecked, because on Mars a broken filter cannot just be swapped next week. A replacement part ordered from Earth takes roughly 3 years to travel out and confirm it arrived, long enough for a sapling planted the day it shipped to already stand taller than the crew member who ordered it. This was the third of the 5 obstacles, and unlike the first 2, it did not hold still long enough to be measured once and set aside. Distance stayed fixed. Radiation, once the dose was known, held roughly steady. The dust was different. It sat in the ground, but it also moved, and what it did once it started moving mattered even more than what it was made of. Mostly, the dust behaves the way any loose grit behaves, drifting a little in ordinary wind and settling back down again within a few hours. But every few Martian years, without much warning, it stops behaving that way at all. Regional storms, some large enough to cover ground the size of a continent, form on a fairly regular schedule, mostly during the Martian southern hemisphere summer, when the planet sits closest to the sun and the temperature difference between sunlit ground and shadow drives powerful winds across the surface. Most of these storms rise, spread for a few days or weeks, and fade back into calm air. What makes Mars different from anywhere else worth landing on is that sometimes, for reasons still not fully understood, a regional storm keeps growing instead of dying out. It merges with neighboring systems and spreads until it wraps around the entire planet. How does a planet with an atmosphere barely 1% as thick as Earth's manage to blot out its own sun for months at a stretch? The particles doing it are the same fine, sharp grains already settling on every visor and seal, light enough to stay aloft far longer than dust ever could on Earth. A storm on that scale happens roughly once every 3 to 4 Earth years, on a schedule too irregular to forecast with any real confidence. When one arrives, it does not simply dim the sky. It can cut the sunlight reaching the ground by as much as 99%. Picture every light in a packed stadium switched off at once, except for a single bulb left burning far up in the rafters. That is close to what Martian noon looks like inside a global storm. The sky itself slides from its usual butterscotch tan toward a heavy, darker brown. Surface temperatures swing as the balance of heat shifts, and solar panels across the whole planet generate almost nothing until the haze finally lifts. Something else was happening. On May 30th, 2018, one of those storms began building over the Martian surface. By June, it had grown into one of the most expansive storms on record, a haze thick enough to swallow entire regions from view. NASA's Opportunity rover had been running on solar power for 14 years by then, a rover originally built to survive 90 days. The storm ended that run. As dust thickened overhead, its panels stopped generating enough power to keep its batteries charged through the long Martian nights, and its last transmission, sent that same June, hinted at a fault caused by starvation of power rather than any mechanical break. Engineers at NASA's Jet Propulsion Laboratory sent more than 1,000 separate commands over the following months, each one a knock on a door that never opened. When the storm finally cleared, weeks later, Opportunity's batteries had drained too deep to ever recover. Wait. One of the most successful missions in the history of planetary exploration was not destroyed by impact, not by mechanical failure, not by distance. It was ended by dust blocking the sun. A human mission would very likely lean on solar power too, at least in part. Full nuclear systems, built and tested for a habitat at Mars scale, do not exist yet, though NASA and the Department of Energy are developing a concept called fission surface power, a small nuclear reactor designed for planetary surfaces that could one day close this gap. Until it does, a solar-dependent crew spending 2 to 3 years on the ground is not gambling against some remote possibility. Run the odds across a stay that long, and the outcome stops looking like chance at all. Somewhere in that stay, a major regional storm will very likely arrive. There is a real chance a global one will too, and unlike Opportunity, the people waiting it out cannot simply power down and hope for spring. What follows from that is not one problem arriving at once. It is several problems stacked on top of each other. Oxygen generation, carbon dioxide scrubbing, water recycling, and thermal control all draw continuously on electrical power, and none of them can simply pause for a few days without consequence. Backup batteries hold only so much charge. What happens when every one of those systems needs power at once, and there is not enough to go around? If a storm drags on for weeks, which these storms routinely do, and the power available cannot cover every system running at full strength, the crew is forced into a choice nobody wants to make, deciding which life support function runs at reduced capacity and which one cannot be touched. At the same time, they cannot step outside to fix anything or simply ride it out under open sky. Reduced visibility, charged dust, and damage risk to equipment rule out surface work during a major storm, so the crew stays sealed indoors, watching consumables shrink and power reserves fall, with no firm date for when the sky will clear. Confinement, dwindling resources, and an open-ended wait, stacked together, have no real training equivalent on Earth. NASA's own human research program lists exactly this kind of behavioral and performance strain, alongside isolation and communication delay, as one of 5 major categories a Mars mission has to resolve before it can be called safe. Antarctic winter cruise, submarine deployments, and the volunteers of the Mars 500 experiment all point toward the same finding: extreme confinement under real stakes wears down judgment, cooperation, and mood together. And it does so measurably, not just in how people say they feel, but in how they actually perform. A crew running on frayed sleep and rising anxiety does not simply feel worse, it makes more mistakes. On Mars, a misread pressure gauge, a missed seal check, or a wrong mixture in a life support line is not a forgivable slip. Not a correctable error. A single failure with no second chance built in behind it. This is the cascade in miniature: power lost, systems triaged, people confined, minds strained, mistakes more likely. The same shape returns later in a wider form once every hazard on this list is finally added together. The storm itself is not the only mechanism doing damage. Martian dust carries its own electrostatic charge, built up the same way static builds when a balloon is rubbed against hair, except here the effect plays out across an entire planet's surface, all the time, not just during a storm. Charged dust does not settle and wait patiently to be swept away. It clings to solar panels, to visors, to seals, sensors, and camera lenses, pulled actively toward every nearby surface the way iron filings are pulled toward a magnet. Any tool, suit, or piece of equipment carried outside and brought back in tracks that charged perchlorate-laden dust straight into the pressurized air the crew breathes. So decontamination has to be constant and exact, never occasional. NASA has studied one possible fix: electrodynamic dust shields, surfaces with a faint oscillating electric field built into them, designed to push charged dust away before it ever has the chance to settle. Lab results have been genuinely promising, but the technology has not been proven at the scale or across the years-long duration that an actual human mission would demand. It is the same pattern radiation ran into earlier: real progress, followed by a gap between where the research currently stands and where it needs to be before anyone stakes a life on it. That closed out the third obstacle in both of its forms: the slow chemical one settled into the ground, and the sudden, planet-swallowing one that rises up out of it. 2 obstacles remained, and the nearer of the 2 was not waiting outside the hull at all. It had been building quietly, invisibly, inside the crew's own bones since the day they left Earth. That quiet building has a name. It starts with gravity, 9.8 meters per second squared. The pull that has pressed down on every cell of every body since complex life first crawled out of an ocean roughly 4 billion years ago. No ancestor anywhere in that chain, not one, has ever lived a single day without it. Bone density, postural muscle strength, the pressure gradients that hold blood and the fluid in balance from head to foot, even the shape of the heart's own chambers, all of it built on that one constant term. Take the term away, and the body does not simply cope, it renegotiates everything at once, and the renegotiation starts in the skeleton. Why bone specifically, and why so fast? Because bone is the one structure in the body built entirely around the assumption that something is always pushing back against it. Bone looks fixed, a scaffold poured once and left standing. It is not. It is living tissue in constant motion, cells called osteoclasts dissolving old bone, while cells called osteoblasts lay down new bone behind them. A demolition crew and a construction crew working the same site around the clock, guided by mechanical stress, the ordinary tug and push of weight and movement. What happens to that arrangement when the signal telling it to keep building simply disappears? The osteoclasts keep working. The osteoblasts slow down. The bone thins. On board the International Space Station, astronauts on a typical 6-month mission lose bone density at roughly 1 to 2% a month in the hips, spine, and lower limbs, the regions that normally carry the body's weight. For comparison, postmenopausal women, among the fastest natural bone losers on Earth, lose about 1 to 2% a year. Astronauts lose that same amount in a single month. By the end of 6 months, a crew member can have lost 7 to 12% of the bone in the regions that matter most for standing and walking. A Mars transit runs closer to 9 months, not 6. Not all of that loss comes back. Some of it does not come back at all. It concentrates in trabecular bone, the fine internal lattice inside the spine and hip, the same kind of scaffolding that keeps a tall building from buckling under its own weight. And that is precisely the bone least likely to fully recover once a crew member is home. NASA astronaut Scott Kelly spent 340 days aboard the station, close to the length of a one-way Mars trip with room to spare, while his identical twin brother Mark stayed on the ground as a living control subject. In 2019, the journal Science published what came out of comparing them: changes in gene expression, in cognitive performance, in telomere length, in gut microbiome composition, and significant measurable bone and muscle effects, some of which were still present well after Scott's return. 340 days was one man, on one mission, in orbit still well within reach of Earth. A Mars crew would spend a comparable stretch simply getting there, then months more on the surface, then the same stretch again coming home, all of it far past the point where anyone could fly up and check. Here's the part most people assume solves itself. Land on Mars, stand on solid ground again, and the body starts to heal. The logic feels sound. Any gravity beats none, weight is weight, and a crew member who has been falling for 7 to 9 months should start rebuilding the moment their boots touch soil. So surely 38% of Earth's pull is enough to help. It helps, just not enough. Mars' gravity sits at 38% of Earth's, and that number lands in an unhelpful middle ground, present but not present enough. Bone remodeling responds to a loading signal only above a certain threshold, the way a light switch needs a minimum voltage before the bulb turns on at all. Below that threshold, the circuit can stay connected for months, and nothing happens. Mars' gravity supplies real load. It likely does not supply enough to push the signal back over that line. A body standing on Mars is no longer in freefall, but it is not back in balance either. Not recovery, a different kind of limbo. Whether 0.38 of a G is ever enough to arrest the decline, not over 6 months but over years, is a question with no answer behind it yet. No human being has spent long enough at that gravity for anyone to find out. The honest answer is we do not know. Exercise helps close some of the gap. NASA has built for it. Resistance machines aboard the station designed to simulate loading against the missing weight. 2 to 3 hours of structured training every day. That schedule slows the loss. It does not stop it. On the station, that time is protected, built into the schedule by ground teams with little else competing for it. What happens on a mission where those same 2 to 3 hours have to be carved out of days already filled with science, maintenance, repairs, and the plain work of staying alive, all of it managed by the same small crew with no backup arriving to help? The time budget is brutal, and on the days it matters most, something in it always gives first, and it is rarely the emergency repair that gets skipped. Muscle goes faster than bone, and it goes first of all. Without gravity pulling against them, the postural muscles that keep a body upright, the back, the legs, the deep muscles of the core, begin shrinking almost immediately. The The soleus, the calf muscle that fires nearly every moment a person stands or walks on Earth, can lose up to 30% of its mass over a 6-month flight, close to a third of a muscle gone that the body has leaned on every day since it first learned to stand. 30% of a muscle gone. No injury, no single dramatic moment. Just steady, quiet absence, doing its work day after day. Even with daily countermeasure exercise, grip strength and leg strength decline as the muscle architecture quietly downsizes itself to a load that is no longer there. Astronauts returning from long stays on the station frequently cannot walk unassisted the moment they land. And full recovery, where it happens at all, takes months, not days. Not fitness loss that returns. Bone loss that does not. Put the two together and the arrival moment comes into focus. A crew stepping onto Mars after 7 to 9 months in transit lands, with thinned bone, atrophied muscle, and a body still recalibrated for weightlessness. At the exact moment, it is asked to perform the most physically demanding work of the entire mission. Unloading a lander, assembling a habitat, walking under a full pressure suit in gravity the body has not felt in most of a year. It is the same shape already seen once before, in the brain, worn down by radiation on the very approach to landing. Now is the body itself arriving weakest at precisely the moment the mission needs it strongest. That was the arrival deficit. Thinned bone, atrophied muscle, and a body still learning to trust its own weight, walking straight into the hardest hours of the whole mission. Not a gradual return to strength. A demanding job handed to the weakest version of the person who left Earth. And bone and muscle were only the two changes easiest to see from the outside. Underneath them, other systems bent by that same missing gravity, fluid balance, eyesight, the heart itself, had been quietly reshaping the entire time, mostly out of sight and largely still unaccounted for. Fluid balance is the first of those systems, and it moves in a direction nobody watching from the outside would guess. On Earth, gravity pulls blood and the fluid that cushions the brain and spinal cord steadily downward, toward the legs and feet, all day, every day, without anyone noticing the work being done. The whole circulatory system is built around that pull, a heart shape to pump uphill against it. Different pressure gradients in the upper body than in the lower, and every organ that depends on those gradients, including the eyes, calibrated to match. Take the downward pull away, and the fluid does not simply settle somewhere new and stay there. It moves toward the head instead, a shift that begins within hours of reaching orbit, and does not reverse until gravity returns. Astronauts describe the early feeling as a head cold that never clears, a constant stuffiness. Sinuses swollen because the fluid that would normally drain downward no longer does. Faces round out. Legs, drained of their usual fluid load, visibly thin. For the first few days, it reads as a cosmetic curiosity. Something to joke about in a crew photo. Puffy above the collar. Thin below the knee. It is not cosmetic. Quietly, with no symptom a crew member would feel day to day, the shift raises intracranial pressure, the pressure of the fluid surrounding the brain and spinal cord. That rising pressure pushes outward against the back of each eyeball, flattening the optic nerve where it meets the retina and folding the choroid, the layer of blood vessels behind it. There is no ache to flag it, no headache that arrives on schedule to warn a crew member something is wrong behind their own eyes. The damage builds in silence, the same way the bone loss did, the same way the radiation dose did on the way out. NASA gave the resulting condition a name: spaceflight-associated neuroocular syndrome, vision damage caused not by injury or infection, but by the sustained, ordinary absence of gravity's pull. Roughly 7 astronauts out of every 10 who fly long-duration missions report some change in their eyesight. In 2016, the New England Journal of Medicine published direct evidence of how deep that change runs. 11 of 27 long-duration astronauts examined showed clinically significant swelling of the optic nerve, and most of the group showed measurable structural change in the eye or brain. Not a subjective complaint written down after the fact. A structural finding, seen on a scan, present whether or not the astronaut mentioned any trouble seeing. That data comes from 6-month station missions. A Mars transit runs closer to 9 months each way, with 2 to 3 years total before a crew sees Earth again. Nobody has measured what that duration does to the back of the eye, because nobody has been exposed to it for that long. What is already known crosses well into concern on its own, and a crew member landing on Mars with degraded vision, mid-descent, mid-repair, mid-emergency, is not a small risk to be carrying quietly. The heart bends under the same absence. It is a muscle built to push blood upward against gravity for an entire lifetime. And in microgravity, with no vertical column of blood left to fight, the left ventricle, the chamber that does the heaviest lifting, simply works less. Work a muscle stops doing. It stops being built for. Studies document a measurable drop in left ventricular mass over long missions, a heart that comes home smaller and less powerful than the one that left. In the twin study, Scott Kelly's heart changed its actual geometry over his year in orbit. A shift his brother Mark's heart, tested on the ground across the same months, never showed. The heart was not simply working differently up there. It was becoming a different shape. A smaller reshaped heart returning to Earth, or landing at a third of Earth's gravity on Mars, meets a sudden jump in demand it spent months quietly adapting away from. The risk that follows has a clinical name: orthostatic intolerance, the plain inability to keep blood pressure steady while standing upright, sitting alongside a broader vulnerability to cardiac strain. Both arrive exactly when the workload peaks. At the moment, boots first meet ground. Then the immune system, quieter than either of the other two, and no less real for it. Research aboard the station, reinforced by animal and ground studies, shows microgravity blunts the activity of natural killer cells, the immune system's frontline defense against infected and cancerous cells. With that defense dulled, viruses the body normally keeps locked away start waking back up. Epstein-Barr, the virus behind mononucleosis; varicella zoster, the virus behind chickenpox, and, later in life, shingles, and certain strains of herpes simplex. A 2019 study found astronauts shedding these reactivated viruses at rates far above matched volunteers who never left the ground, often with no symptom at all to warn anyone it was happening. On Mars, a weakened immune system does not sit by itself. It interacts with the radiation, which independently damages immune cells and bone marrow, and with the psychological weight of isolation, which research links to immune suppression of its own. Layer those together and the vulnerability compounds, with the nearest hospital not an hour or a day away, but a return trip of roughly 3 years, effectively a hospital on another planet. None of these three, the eyes, the heart, the immune system, are the visible damage. A crew member can watch their own bone density drop on a chart and understand, in a straightforward way, what has been lost. Nobody can watch their own optic nerve flatten, or their own left ventricle lose mass, or their own dormant viruses stir awake. These changes are measured on other people, in other studies, and then applied forward. An inference about what is probably also happening, quietly, inside the body, doing the actual mission. Here is where the 3 threads meet. First, the fluids shift, and the eyes and the brain absorb structural damage that may not announce itself until the moment sharp vision matters most. Second, the heart shrinks and reshapes itself, and the cardiovascular strain peaks exactly when arrival asks the most of it. Third, the immune system quiets, and old infections stir back to life at the worst possible moment to fall sick. None of this happens in isolation, not in the body, and not in the sentence describing it. It happens all at once, inside the same person, across the same years. What happens when a damaged immune system meets a body already carrying a radiation dose? What happens when blurred vision meets a mind already slowed by the same radiation? NASA's own human research program has a name for what results when systems like these fail together instead of separately: the integrated risk problem. Radiation on its own is dangerous. Immune suppression on its own is dangerous. Radiation and immune suppression together are more dangerous than either alone, because a weakened immune system cannot clean up what damaged DNA leaves behind. Cognitive impairment from radiation-damaged neural tissue is one hazard. Vision loss from fluid shift damage is another. Cognitive impairment and vision loss together in the same person during the same landing is not simply two hazards stacked. It is a different and harder problem, one that resists modeling and resists a clean fix because there is no single system left to repair on its own. Not 5 separate risks arriving on 5 separate days. One body absorbing all 5 at once for years with no one arriving partway through to check the math. A mission plan can list each hazard on its own line, give it its own study, its own countermeasure, its own paragraph in its own report. The body does not read the report that way. It carries every line at once in the same bloodstream on the same day. Bone and muscle, at least, show up on a scan. A density number, a mass percentage, something a flight surgeon back on Earth can point to and track across the mission. What comes next resists that kind of measurement almost entirely. The isolation, the silence, and the slow weight of knowing that none of it can be undone by simply turning around. What comes next resists a chart in a different way than bone density or a radiation badge ever did, because it was never built to sit still and be measured. Long before anyone drew up a Mars itinerary, other extreme places had already taught researchers what happens to a mind that cannot leave. Antarctic winter crews sit through months of total darkness at 80 degrees below zero. Submarine crews run silent at depth for stretches with no sky at all. Isolation chambers built for exactly this purpose have held volunteers for as long as ethics boards would allow. Militaries and space agencies study these environments for a practical reason. They need to know what breaks a person and what keeps one working. What the data shows back is not comforting, but it is, in the phrase researchers themselves reach for, profoundly human. In June 2010, 6 volunteers, 4 Russian, 1 French, 1 Italian Colombian, sealed themselves inside a facility outside Moscow for 520 days, close to a year and a half. The Russian Institute of Biomedical Problems ran the program together with the European Space Agency, and the goal was simple to state and hard to endure. Simulate the psychology of a full round-trip Mars mission without ever leaving the ground. The interconnected modules totaled about 550 cubic meters, a shared living space smaller than many family homes, split 6 ways for a year and a half straight. No windows, no fresh food, no going outside. Every message in or out was deliberately delayed by up to 20 minutes, matching, on purpose, the lag a real Mars crew would live inside. What happened over those 520 days was not a dramatic breakdown. It was quieter than that, and in some ways more troubling. Sleep patterns deteriorated across the crew. Several volunteers slipped into what researchers called a sedentary pattern, spending more and more time simply lying down, a slow retreat into inactivity that shows up again and again in people facing a monotony they cannot escape. Physical activity dropped. Cognitive performance on standardized tests declined in some of the 6. Small frictions between crewmates ground against each other in what one report called a subtle grinding manner. Not blow-ups, just wear. One volunteer showed a pattern closely resembling a mild depressive episode, real and measurable, sitting right there in the data. Here is the part no simulation can rehearse. Every volunteer in that facility knew something a real Mars crew never will, that the walls could open. Somewhere behind the sealed door was Moscow, then Russia, then home, reachable the moment anyone decided the experiment had gone far enough. Not an actual crisis, a rehearsal for one. A real Mars mission carries no such door, and no version of the experience that can be called off partway through. Decades of Antarctic winter over records add a second dataset, drawn from stations like McMurdo and, in far greater depth, Concordia and Vostok. split a long winter stay into quarters, and the worst stretch is never the one people expect. Not the disorienting first weeks, not the final weeks with the finish line in sight. The third quarter, the long middle after the novelty has burned off and before the end feels close enough to hold on to, is where distress peaks, where conflict peaks, where cognitive performance dips hardest. Researchers have a name for what happens there: psychological hibernation, a kind of semi-conscious withdrawal, engagement dropping away as self-protection against a situation nobody can change by trying harder. People go quieter, more irritable, less motivated. A crewmate's eating habits, a recurring hum from a vent, a difference in how two people organize their tools. Any of it can curdle into real conflict, because on a research station, same as on Mars, there is nowhere to walk away to. Stretch that pattern across a Mars mission, and the timing turns cruel. A full mission runs 2.5 to 3 years. The third quarter of the surface stay lands in the middle of it, and the middle of a surface stay is exactly when a crew attempts its hardest, most physically demanding work. The period of lowest psychological reserve and the period of highest operational demand are not separate stretches on the calendar. They are the same stretch. Not an unlucky coincidence. A structural feature of the mission itself, with no drug and no training program that fully resolves it. Layered on top of that timing is a gap already familiar by now: the minutes a signal spends crossing the space between the planets. That delay does more than slow a conversation. It changes what a conversation even is. There is no real time call home. No working through a hard night with a partner in the same breath. Every message becomes what people who have lived with it call a time capsule, sent, then held in transit for the better part of an hour, answered by someone who has already moved on to whatever came next in their own day by the time a reply arrives. Documented across Antarctic postings, submarine deployments, and Mars 500 alike, that lag breeds a specific kind of disconnection. People reach out less, exchanges turn shorter and more formal, and over 2 or 3 years, the sum of it becomes something researchers call existential aloneness, surrounded at all times by the only handful of people who count as neighbors, colleagues, and society, all at once, with no relief and no rotation. The isolation leaves a mark that shows up on a scan. Researchers at Harvard Medical School, the University of Houston, and several European space medicine institutes have been mapping it for years, and the clearest evidence again comes from Antarctica. A 2019 study in the New England Journal of Medicine, led by researchers at the University of Pennsylvania, measured a brain structure called the dentate gyrus, part of the hippocampus, in 14 scientists before and after a roughly 14-month expedition. The average reduction was 7%, a small number to read off a page. In a structure that governs memory, learning, and spatial navigation, 7% is closer to shaving one thin corner off a piece of fruit already too small to lose much from. A sliver gone from something the mission needs to stay whole. The same study found lower levels of BDNF, brain-derived neurotrophic factor, a protein essential to keeping neurons growing and repairing themselves. 7% is measurable, 7% is real, and nobody has measured what 2 to 3 years does, because nobody has been isolated that long. Scientists describe a related concept called cognitive reserve, the brain's built-in buffer against damage and stress, and it varies with genetics, education, and general health. Under ordinary strain, most people draw on that buffer without ever noticing it is there. Under sustained, severe stress, the buffer erodes layer by layer. A mission with zero room for error depends on a crew holding onto exactly the resource the mission itself spends 3 years quietly depleting. What happens to a decision made under all of that, at the exact moment the mission needs it made well? Some of this can be softened. Virtual reality systems built to simulate open sky and moving weather. Private spaces designed with real psychological input. Counselors on Earth recording video messages timed to arrive when they will do the most good. All of it helps at the margins. None of it reaches the actual problem, because the actual problem was never a design flaw waiting for a better fix, not a hardware gap. A mismatch between an animal built for open sky, shifting seasons, and constant sensory texture, and a sealed box that offers none of it. Distance, radiation, dust, and gravity each left a mark you could weigh, photograph, or read off an instrument. The mind is the fifth hazard laid out since the very beginning, and it works differently. It leaves marks too. They just do not sit still on a chart the way a bone scan does, and the hardest one to measure may be the one the mission relies on most: whether a creature shaped by one planet can stay whole on the near-perfect inversion of everything that shaped it. And on Mars, the question of what happens when a mind finally reaches that limit is never abstract for long, because the same distance that isolates a crew is the distance that decides what happens the moment a body fails too. A body failing on Mars starts out looking exactly like a body failing anywhere else. A pain that will not ease, a fever that keeps climbing, a cut that will not stop weeping. What changes is not the symptom. It is everything that happens after it. On Earth, planners have a name for the thing that decides whether a symptom becomes a story or a tragedy. Time to definitive care. How long from the first bad sign to a facility that can actually treat it? In a city, that number is 15 to 30 minutes by ambulance. Close enough that most people never think about it at all. In deep wilderness, it stretches to hours, already enough to worry a rescue team and change how a hiker packs a bag. At an Antarctic station like Concordia or Vostok in the dead of winter, weather can push it to days. A stretch field doctors already treat as the outer edge of what medicine can promise anyone. Line those up and a pattern appears before Mars even enters the picture. Minutes, hours, days, then Mars. Not another rung on the same ladder. A different ladder entirely, because on Mars the honest answer is years. Every other word on that list still means something close to what it means at home. Urgent still means urgent. Serious still means serious. Only the last word changes its meaning completely, because a wait measured in years is not really a wait for care at all. It is a redefinition of what care can even mean, once the option of reaching it disappears. The return trip alone runs 7 to 9 months. The same stretch of time already sat with once, now carrying a different weight. Most surgical recoveries resolve inside it many times over. Most cancer treatments run their full course and finish long before it ends. A heart attack, a serious infection, a bad fall against sharp equipment. All of these are survivable on Earth, mostly because care arrives immediately, often within the same hour the symptom appears. Move the same events to Mars, and the same 9 months that once measured a journey now measures how long a crew must manage the problem entirely on its own, with whatever is already on board and nothing more. A 2020 study in NPJ microgravity looked at exactly this question. What actually goes wrong in a body over a mission this long? And the list it produced was almost disappointing in how ordinary it read. Dental emergencies, kidney stones, irregular heartbeats, urinary infections, torn muscles and strained joints, psychological crises severe enough to need direct intervention. Nothing exotic, nothing pulled from a disaster film. These are the things that happen to healthy adults in their 30s and 40s over the ordinary course of 3 years. The kind of events a clinic back home handles by lunchtime and forgets about by dinner. None of these conditions are dangerous because of what they are. A kidney stone is a kidney stone anywhere in the solar system. What makes the list frightening is not the biology at all. It is the setting. A habitat with no specialist down the hall, no imaging center a short drive away, and no second opinion that can arrive before the situation has already resolved itself one way or another. The constraints stacked against a Mars crew are not a failure of planning. They are closer to a law. The medical kit holds a finite set of supplies, decided months in advance on a launch pad, and impossible to restock once the hatch seals. The crew's training, however serious, however many hours logged in simulation, stops well short of a working surgeon's years of hands-on practice. The communication delay rules out any real conversation with a specialist in the exact moment it would matter most. And there is no evacuation. Not a slow one, not an expensive one, not one held in reserve for the worst case. None. If a condition outgrows what the crew can manage on their own, the answer was never going to be a rescue flight. It was always going to be manage it with what is on hand, and hope. Picture it directly. A crew of 5, 4 months into their surface stay, past the midpoint, deep in the same low stretch that studies of isolation keep locating right about here. The third quarter, the quietest and heaviest part of the mission. Bones already thinner than the day they launched. Muscles weaker. Vision, for some of them, already subtly changed. Immune defenses already running below their Earth baseline. Into that already strained body, one crew member wakes in the middle of a sleep period with abdominal pain that will not settle. It sharpens over the following hours, moving and tightening in a way that will be familiar to anyone who has felt it before. The medical officer, trained as a flight surgeon but not a specialist in the gut, examines the pain and reaches a conclusion nobody on board wanted to hear. This looks like appendicitis. On Earth, that diagnosis barely raises a doctor's pulse. It is one of the most routine operations performed anywhere, done successfully thousands of times a day in hospitals that barely pause to note it. Not routine here, different entirely. The kit includes a surgical set, and the flight surgeon has actually trained specifically and repeatedly for this exact procedure. But a pressurized Martian habitat is not an operating theatre. Anesthesia under partial gravity has barely been studied at all. How gases settle, how a patient's airway behaves, how anything that normally depends on a gentle downward pull performs at a third of it. Infection risk is already elevated by an immune system running under strain from months of radiation and isolation before this night even began. Sterility, the kind an Earth hospital takes for granted without a second thought, cannot be fully guaranteed inside a habitat that is also a bedroom, a laboratory, and a kitchen. They send a message to Earth requesting a specialist. The current delay runs 18 minutes each way, so an answer comes back 36 minutes after the message goes out. From physicians working only from a spoken description and whatever images made it through the connection, unable to press a hand against the actual abdomen or run a single test of their own. What comes back across that gap is real expertise, offered honestly and in good faith. What it is not, and cannot be, is a decision. The choice of whether to operate and when and how belongs entirely to the people standing in the room, because any further back and forth would outlast the emergency itself. Not a decision reached together. A decision made alone, with company waiting patiently at the far end of a very long silence. This is not a worst case dressed up to alarm anyone. A 2015 paper in aviation, space, and environmental medicine studied medical event rates aboard the International Space Station and extended those rates out across a Mars-length mission. Its conclusion was blunt, stated without hedging. At least one potentially life-threatening medical event should be expected over a mission of that duration, even inside a crew screened and selected for their health beyond almost any other profession on Earth. Not a possibility to plan around if convenient. An expectation to plan for as a certainty. So the people inside that habitat, holding a finite kit, a training that stops short of specialist skill, and bodies already worn down by everything the mission has already asked of them, are not backup. They are the entire medical team the patient will ever have, from the first symptom to whatever the outcome turns out to be. And none of this, the years instead of hours, the medicine practiced alone in a sealed room, the answer that cannot arrive in time to matter, exists apart from the reason it can never be fixed halfway through a mission already underway. That reason is not medical at all. It sits in the sky, in the slow, indifferent turning of two planets around the same sun. A piece of celestial bookkeeping that decided all of this long before any crew ever left the ground. Once you actually look at that turning, the whole shape of the mission becomes obvious. The numbers behind it look almost harmless on a page. 54 million kilometers at the closest pass, over 400 million at the farthest. A spacecraft cannot simply fly the short way whenever it likes. It has to catch Mars where Mars will be, not where Mars is standing now, so it follows an elliptical, fuel-saving path called a Hohmann transfer, launched at one precise moment, coasting for 7 to 9 months until the two orbits finally meet. That transit itself was covered already. What matters here is what happens on the far side of it. A crew that lands cannot simply turn around and fly home the following week. The planets have already moved on without them. The next window, favourable enough for the return trip, does not open for something like 14 to 26 months, depending on the exact path chosen. So the surface stay runs 500 days at minimum, sometimes well past 600, before the return leg even becomes possible. Add the outbound transit, the surface stay, and the trip home, and the full mission runs 2.5 to 3 years, from the moment the engines fire to the moment boots touch Earth again. None of that is a worst case. It is the ordinary plan. And the launch itself only opens once every 26 months, a narrow calendar slot dictated entirely by where the two planets happen to be standing in relation to each other at that moment. Think of it as a single departure gate that opens for a few weeks and then locks again for more than 2 years, no matter how ready the crew, the rocket, or the funding happen to be. Miss it, and there is no make-up date the following season. There is only the same wait again, all over, more than 2 years long. Earth circles the Sun in roughly 365 days. Mars takes almost twice that, close to 687. Because the two planets move at such different speeds, their relative positions never hold still, and roughly every 2 years, the geometry lines up in the worst possible way. Mars slides directly behind the Sun as seen from Earth, an alignment called superior conjunction. The Sun is not a quiet neighbor to sit behind. Its corona floods the surrounding space with plasma, charged particles, and radio interference strong enough to degrade or destroy a signal trying to pass through it. For a stretch of 2 to 4 weeks, depending on the exact geometry, nothing gets through at all. Not delayed, not degraded, silent. NASA already knows exactly what that silence looks like. During the 2022 conjunction, mission controllers on Earth stopped sending commands to every active machine on or around Mars, Curiosity, Perseverance, the small helicopter called Ingenuity, the InSight lander, the orbiters overhead, all of it, for close to 2 weeks, because a corrupted command sent through that interference could have damaged hardware nobody could reach to repair. That was robotic caution, exercised on machines nobody had to feed or comfort. Apply the same blackout to a living crew and the picture changes completely. No messages in, no messages out, no mission support, no medical consultation, no counselor's voice, no news from home, no way to send a distress call and expect an answer inside any useful stretch of time. Depending on how the mission is timed, a crew on the surface might live through one of these blackouts. A longer stay could mean 2. Relay satellites positioned off to the side of the Sun could someday soften the edges of that blackout, catching a partial signal around the interference rather than through it, and crews already trained for full autonomy, with decision frameworks and emergency protocols built in advance for exactly this kind of gap. None of it changes the core fact. For weeks at a stretch, the crew operates with no outside input of any kind, in an environment that forgives almost nothing, making the kind of decisions that on Earth would involve a room full of specialists standing by, consulted before anyone touched a single switch. What does that moment actually ask of the people living through it? Researchers who study decision-making under extreme uncertainty, drawn from military special operations, deep wilderness expeditions, remote industrial sites, describe a consistent list: clear thinking, steady emotional control, careful analysis under pressure, the ability to weigh options with no one outside to check the reasoning, and the willingness to commit to a high-stakes choice on incomplete information. That is precisely the set of abilities this mission has spent years quietly wearing down. The radiation dose already reaching the brain before landing. The sleep, broken by isolation. The memory center measurably smaller after years of sameness. The quiet pressure still resting on the optic nerve. Each of those was a separate finding in a separate section. Here they converge on a single moment, a crew cut off from every outside voice, asked to think most clearly at the exact point the mission has left them least equipped to do it. Not a flaw some engineer failed to catch. A structural feature of the architecture itself, built in from the moment the orbits were chosen. There is one more piece the orbital mechanics decide, and it is the most absolute of all. If something goes wrong in the first weeks after launch, badly wrong, there is no quick way back. The planets are not in position for it. Turning around onto a faster path home would demand fuel reserves no version of the mission plan actually carries. Past a certain point, the most fuel-efficient way home no longer runs backward toward Earth. It runs forward, through Mars, into orbit around it, and into the same long wait for a return window that a completed mission would have faced anyway. The crew is committed from the moment they leave Earth orbit. You have left. You cannot come back early. The only way out is through the mission itself. This is why psychological screening for a Mars crew reaches further than anything used for the space station. The station always keeps a capsule waiting, a door that can open in hours. Mars asks something else of the people chosen for it. Not simply whether they can perform the work, but whether they can carry out that work for years, while knowing, with total certainty, that there is no way out early. No emergency flight home, no changed mind, no door. The selection process is no longer only asking who is skilled enough. It is asking who can hold that knowledge quietly for 3 years without it hollowing them out. There is an old comparison worth sitting with here, and it is worth being honest about where it holds and where it quietly does not. Centuries ago, sailors pushed wooden ships past the last visible edge of the coastline, out into open ocean with no guarantee the voyage would end anywhere but the bottom. They had no way to call home, no way to know, for months at a stretch, whether the people who loved them were still alive, or whether they themselves would be seen again. There is something genuinely moving in that. Humans have always pressed forward into places that offered no promise of return, and something in the species keeps doing it, generation after generation, because staying inside the known edge of the map has never once been enough. But those sailors were built for the ocean in a way no human body is built for Mars. Their skin, their lungs, their muscles, all of it still worked exactly as evolution intended the moment they finally stepped back on deck. Their crossings, however dangerous, ran months, not years. And when the sea did take a ship, the tragedy, however devastating to the people who loved that crew, stayed finite. It ended, one way or the other, within a season anyone waiting on shore could still measure. Mars offers none of those mercies. The body degrades in ways the ocean never touched. The isolation runs longer than any voyage in maritime history. And if something goes wrong out there, in ways this story has tried to lay out honestly and without exaggeration, there may be no ending at all. Only years of a problem nobody on the planet can reach. And still, somewhere on Earth tonight, a mission planner is bent over the same orbits, waiting for the next window to open. The same pull that once sent wooden ships past the edge of the map, now aimed at a small red point of light that keeps turning quietly overhead, whether anyone below is ready for it or not.